Hello everyone, I'm Ulo from Peking University, and I'm glad to have this opportunity to present our work in NDSS 2022. The title of our work is ScriptChecker to turn third-party script execution with task capabilities. And our work talks on restricting third-party scripts. The third-party scripts usually provide many ready-to-use functions for specialized utilities and web page feature enrichment, such as using the jQuery, CryptoJS, and many advertisement scripts. They are greatly attractive to web page developers, and hence a web page usually include multiple third-party scripts, although they have different developers. This picture shows an example where the web page includes 3 third-party scripts and using the HTML script tag. And interesting enough, the browser security policy with the third-party script and the host script has the same principle when performing the access control. For instance, the where orange policy does not distinguish the third-party script from the host script. So security concern will arise when the third-party script is malicious. Some existing works has analyzed the security threat. For instance, in 2017, the researchers found that nearly 37% of the top 75,000 websites contain at least one version of third-party scripts with known vulnerabilities. So once a web page introduces malicious script, the malicious script can do whatever the host script do according to the current browser security policy, such as accessing page content, cookie, and network resources, and browser properties. So can a web page restrict the third-party scripts? Of course, a lot of existing work has been done to solve this problem. We call the first type of existing work is as function filter approaches. The basic idea is that the host script has to register advanced functions for each concerned function APIs before executing the third-party script, and each advanced function has a filter to enforce the host script policy. And next, after that, when a third-party script executes these functions, the modified JS engine will execute the advanced function firstly, and only if the advanced function returns true, the JS engine continues to run the previous function. The second type of existing work is named as reference restriction schemes. Their basic idea is to restrict the third-party script ability to reference JavaScript objects by using a special context or dedicated JavaScript scope. So as a result, the third-party script cannot reference the JavaScript objects in the host and must use some person message API or proxies to send their requests. Then the host script can use the API stops to examine the request and make access control decisions. However, both of these two kinds of existing works have some shortcomings. One security concern is that they need to cover all attack vectors. Achieving complete coverage on the attack vectors is highly demanding, error-prone, and requires to re-examine the attack vectors when the JavaScript updates. The second security concern is the confused deputy attack. In this attack, the third-party scripts can leverage its legitimate execution to misuse the host script and as a deputy to access the resources. The deputy may be some other thin orange friends called all functions rightfully access to the third-party scripts, and the third-party scripts may conclude, so one script can use another script as a deputy to breach the restriction. And besides the security, the existing work are not adaptively. According to the list privilege principle, different invocation of the same script could be subject to different restrictions, but the current work cannot do that. Different from the existing works, our approach does not solve the problem from the perspective of JavaScript, so as to avoid the problem of incomplete coverage. We rely on the existing security monitors in the browser. So the web page developers only needs to define the security policies concerning the web-sensitive resources, and they are relieved from the burden of going through each relevant JavaScript API. And secondly, our approach treats the task of JavaScript execution instead of the scripts as a subject requesting resource access. And we separate the host script execution and third-party script execution into different tasks. Then we also make sure the task of host script execution spins of a new task to execute third-party scripts will be assigned with different privileges dynamically. This function here is an example of the tasks. The blue square is the web page host script, and the red one is the third-party scripts functions. The host script may invoke functions from the third-party scripts, read the result, and do some remaining works. Currently, all these functions belong to the same task, and but in our approach, this execution flow is split into three tasks. The second task runs risky script function. The host script can assign privileges to this task, and the entire execution of this risk script will be restricted, even in the case of confuse-deputy attack. And with our approach, the web developer can restrict the third-party script much more easier because she only needs to specify privileges to this risky task. In a word, the existing work relies on the modified JS engine to perform a context-sensitive access control, but in our approach, the ScriptChecker solves the aforementioned issues by making use of the security browser security monitor to do a task-based access control against the web resources instead of the JavaScript APIs. In the architecture of ScriptChecker contains three components: a capability-based discrimination access control system against the task, and a set of APIs that asynchronously invoke the third-party scripts in a new task with restricted privileges, and a sandbox context for third-party scripts for the purpose of context segregation. Next, we will introduce these three components one by one. So the basic unit in task-based capability system is a task. Task is a schedule unit within browser thread. For example, the cron implements task queue and schedule tasks found the FIFO policy. And a task can trap into the JS engine to execute JavaScript code, and that task finishes after the entire JS execution is done. For the task capability, our system ensures that a task by default is not restricted, and JavaScript can create a new child task with restricted capability using our new APIs. And considering some JavaScript API can create a new task, our system ensures that the child task privilege cannot exceed its parent task. So for the capability enforcement, we view the access control subject is a task accessing a resource, and the browser will check the task capability before the browser security monitor. So failing the capability check means to reject the access directly, but passing the capability check only means to the access will be checked by the browser's existing security monitor. Note that the confuse-deputy attack is defeated laterally because since the deputy code runs in a task whose capability cannot exceed the task executing the kernel JS code. The second component is the task-based asynchronous execution. This picture shows an example. The function myfunc is the synchronized execution version. It invokes the function for from the third-party script, get the results, and handle the results. The funny function is the asynchronized version. Here we use a new API to create a task for the risky function 4 with the capabilities no cookie access, And then there is another new task is created to handle the results returned by the risking function. Here is a task queue maintained by the browser. The synchronized myfunc is running the current task, and the two newly created tasks will be put into the header of the task queue to maintain the same semantic with the synchronized function invocation. The last component in our approach is the context segregation. It targets on prevent the environment pointer attack. We put the host script into the main context and put the third-party script to the Thunderbolt context. Unlike the web worker context, the Thunderbolt context has the same API and objects with the main context, so a third-party script does not need to be modified. Since the contexts are isolated, so the environment pointer attack can be defeated. We also allow the cross-context communication. For this communication, the security monitor checks if the main context accesses the sandbox context. The security monitor will return true, allows this access. But if in the opposite direction, we add a new permission in the task capability to organize a whitelist. Only objects in the whitelist can be accessed by the third-party script. And due to the complexity of web, we have some special treatments targeted on the event listener, IPC message, the jQuery, and some inline scripts. Some more details, please refer to our paper. We have built a prototype based on the Chrome 67 and add around 2200 source code. And the source code is available in the GitHub. Here is an example showing how the web developer use our approach. Firstly, when embedding the risky script, the developer shall tag it as risky and specify capabilities. And secondly, the developer can mark some down elements as sensitive, so the task with down access protective capability cannot access it. And finally, when the developer wants to invoke a risky function, she needs to use our newly added APIs. We invalidate our security achievements using the ScriptChecker. The first script is use the dataset from the GitHub, which includes 1,000 malicious scripts. For each script, we build a web page and assign the most restrictive privilege to it. That is no DOM cookie and network access. The results show that 1,022 scripts are blocked, and the remaining 300 scripts fail to execute due to the non-existent APIs. The second script is an empirical study on the Alex top 1,000 sites. We modify the Chrome to label all third-party scripts as risky and label the DOM objects as sensitive if it contains the keywords from this directory. And we found that 4,000 pages in the Alex top sites show that we tested 4,000 pages in the Alex top 1,000 sites, and the results show that 716 domains with either DOM or cookie invasive scripts. We also compared our approach with the existing works from the perspective of usability, security, and performance. The results show that since our approach focuses on the resource to protect instead of the currently covering all attack vectors, the developer actually use to restrict the third-party scripts more easier. And the script for the in terms of the security, since our approach has a built-in combines the tasks with capability, so our approach has a built-in resistance against the computer deputy attacks. And our performance experiment show that our security and the usability advantage are gained at the cost of modest performance loss. And that's all. Thank you.